Hi, and welcome to today's webinar all about simulation. I'm Lizzie Greiner, and I'm a simulation specialist with DesignPoint. Today I'll be diving into several issues that many engineers and manufacturing industries face, maybe on a day-to-day basis, that can be solved with simulation. Here you can see some of the major issues in those industries that affect not only the engineers, but as well as the business owners and everyone involved in the company. And none of this is new. It's all issues that we've seen over the years and will always be a problem if we don't make efforts to reduce them. So we're going to be looking at ways to potentially decrease those frustrating material costs, as well as those random sporadic failures that occur in the field. The product I'll be using as an example is this bike hitch that you see here. It's a simple product used to store, well, bikes on the back of your car. You can easily equip it, and it's simple in theory. Just put the bikes in and take her wherever your car can go. And this is a good example that I'll be using because it can have all of those issues that we discussed in the previous slide. So I'll be using simulation and take this product and create the best version of it. Essentially, trying to make it, well, cheaper, lighter, and more durable. Here you can see I've created a CAD model of this design, and that's what we'll be using with the simulations moving forward. Specifically for this webinar, and for the studies that we're going to be doing, I'm going to be testing this hitch for its performance, so how much load it can actually endure. Also testing to see how many years it can last for and what kind of environments it can be used in, so I can make the correct investment the right time around. All while trying to save the company some money, so trying to worry about those high material costs and things like that. Now here's a little sneak peek of the results that we're going to be looking. We're going to be pushing this to the limit and understanding exactly how it's going to deform, as well as taking a look at those critical areas that can cause this to fail. We'll even be able to understand how this hitch performs, say, when going over a sudden bump that you can see here. So let's jump into SOLIDWORKS and find out how to perform these tests. A typical road bike weighs about 15 pounds, and we'll use that with our studies moving forward. Now the first study that I'm going to show is what I call an initial study of the design. This is before making any changes to get an understanding of where those critical areas are, where it might break, and where I can make some easy changes, as well as giving us some starting numbers to work with moving forward. Now here you can see I've stripped the two bikes, since we're just going to use the weight of those in this actual study. The first step to every simulation is setting up the material. The material is important because some materials are heavier and more durable, but they also cost more than others. So that's something that we're going to be working with today. To start, we're going to assume that it's carbon steel. And you can see we have filled in values that SOLIDWORKS gives us so that we don't have to hunt down those numbers on our own, giving us important numbers such as the density as well as the yield strength of where it would break. Taking a look at the rest of the study here, I've also stripped the model of any pins and bolts that were applied, and I've actually went ahead and applied them as virtual components. This allows me to reduce the model but also maintain the support that the components give to the structure. Next, I've added in some context to define where the weld points are, as well as how the other components behave when they come in contact to each other. Since they are pinned together, they don't need to be welded as well. And finally, I applied a fixed geometry where the hitch would apply to the car and the load that those two bikes push on these two arm pieces. Now upon running the study, I have several results to look at that can give me an idea of the maximum stress and where it is located. So I can see where those critical areas are and where I might want to make some design changes, as well as where some of the low stress points are, where I know that I can do a lot of design changes to. I can also get an understanding of the deformation, where the maximum point is, just to get a better understanding of this overall design. And probably one of the most important And useful plots is a factor of safety, which will tell me how much room I have to make adjustments and still be safe. Here you can see the minimum factor of safety is about 5.2, which is relatively high. It's staying above that critical point of 1, which indicates that this model has not failed, it is not broken in any way. The loading has not permanently destroyed it or deformed it. And also I can get an idea that a factor of safety of 5, I have some room to work with to still stay above 1, but to be able to make some changes to it, which might cause it to dip down a little bit. And finally, again, to get some more reference points and numbers to work with, I want to get an understanding of how much this design weighs with its initial design as well as its initial material. So I can get its mass properties, and here I can see it's roughly 34 kilograms for this rough design. Typically, engineers will stop at this point since we can see that it has passed the study and it works for its intended function. However, we can use simulation to optimize this design while still meeting its performance, so let's take a look at what we can do. Using the results we just saw, I've created another design here. One of the main changes made was in this support structure. I cored out the middle since in the stress plot I could see this was an area with a low amount of stress. I also reduced the thickness of some of the beams by about 1/4 of what it originally was. And the final step to the changes I made was in the material. I changed the material to an aluminum alloy. Aluminum is significantly cheaper. It's not as strong usually, but again, this is something that we will test to see if its strength still can hold up. The study setup is the same as before, with the bolts and pins added in, as well as the contacts, the fixtures, and the force. So we can go right ahead to running this and taking a look at the results now with our updated model. Here I can see the maximum stress has increased, which makes sense since we made some changes to the design. The maximum area is right around the same area, which is also good since it hasn't jumped to any areas that changes were made. Again, I can look at the displacement. The number on that increased slightly, but you can see that it's still relatively in the same area. No changes have made there. And again, we will look at the factor of safety plot, which gives us a lot of insight into maybe some more changes we can make, as well as the progress that we have seen. So let's take a look at the minimum value we see. It's about 1.2, which is still above the 1, the critical point of 1, which means that we have maintained the performance that we saw before. So this will not break with the load that we see it, essentially telling us that the changes we made are valid. We do have less wiggle room, less of a margin above 1, so we could probably say that this is our most optimized design that we can get it down to. And so with that, since we can confidently say that this new model is in fact strong enough to hold up these bikes and meets the same performance as the previous design, let's take a look at the mass of it now with the changes that were made. And you can see that the number has reduced to about 1/3 of its original value, a significant drop in mass, which is going to play a huge role in the cost, as well as how long it can take to manufacture, and even on the consumer side, being able to load this easier for them, which could be a big selling point for this product. Just to sum up initially what we have set up here, you can see that the different iterations we made, we cut down again on the thicknesses material you can see in the beam, as well as that different support structure that was made. Those changes alone reduced the weight you can see from 34 kilograms to 11 kilograms. It's due to the less material involved, as well as the different material, the aluminum being lighter. You can see the maximum values changed, which makes sense due to this different model, but you can see both factor of safety still above that critical value of 1. So even though there was a significant increase in stress, it's still being able to perform to what it needs to be. Another thing engineers do not think of when testing their product is ensuring it can withstand all environments it can be exposed to. I personally like to bike all year round, so that involves the dead hot summer days and the freezing cold winter months and everything in between. Simulation can quickly test in these environments, so we can be sure that this hitch will not fail when exposed to that. This also helps on the company, since they can push out more accurate warranties with tested results, and it can potentially reduce any serious recalls or refunds due to improper testing that wasn't done. So again, we have our optimized design with that support structure and a thinner ball thickness. We have our aluminum alloy, since this is the design that we want to test in all possible scenarios. Our setup is completely the same as well. Same fixtures, same load. We're still loading the same amount of bikes on the back. But the only other change that we make now is inducing a temperature load. And we're going to induce about 120 degrees Celsius, representing a pretty hot day, maybe in Arizona or North Carolina. And we're going to apply it to the entire hitch, since that's where the temperature is going to be exposed to. So now the temperature can impact the integrity of this material, so that's what we want to test for, to make sure that even with these changes that it's not enough to push it over its limit and start to fail on us due to this heat. So again, we run this study with now temperature involved. We can look at the stress value. The max value has jumped up slightly, which is due to the temperature impacting the material. The maximum location is still about in the same area, right where those pins are located, which makes sense here and doesn't give us any worry. We'll jump right to looking at the factor of safety plot to ensure that it is above that critical value of 1, and you can see here that the minimum value is just slightly over 1. It's about 1.1. If it had dipped below that critical value of 1, we would have to go in and make some design changes to it, because even though it had passed our first test with just the bikes, we wouldn't want this to be the final product, since it cannot survive in this hot. But fortunately, we do see that it is above that critical value of 1. So again, this optimized design with aluminum and the roughly 11 kilogram weight can sufficiently perform when in these hot summer days. And now I'll test for the opposite, the extreme cold weather that I bike through. The setup again is going to be completely identical to the temperature we just did. Same model, same material, same connections, same loading, except this time the temperature load that we're going to give it is going to be at about -10 degrees Celsius, which represents a pretty cold day in New York, I would say, maybe up in Alaska a little bit, over the entire hitch again. Now the results for this we'll take a look at. The stress value is similar area of about where the pins interact with the model. A little bump in stress due to the cold interacting with the material and how that affects the integrity. A slight bump there. And we'll take a look right at the factor of safety to make sure it is above that 1, and a minimum value of 1.14 roughly above that 1 value. So we can again say that it is safe to function. It meets its performance value being above that critical value of 1. So in this case, we just quickly tested both hot summer day and a cold winter day. So I can be sure that it's used in all environments, all seasons that I want to use it in, and that way it can put me at ease. So when I go take my bike out, put it on the hitch on those winter days, summer days, that I don't have to worry that this is going to break on me, because I can see here by virtually testing it, it can give me confidence. And again, putting this as an accurate warranty for the company so you can get a range of how this hitch should be used in its proper environments. So not only do I ride all year long, but I also like to mountain bike, which means the trek up the mountain can be pretty bumpy. I want to make sure that this hitch will not break when enduring those kinds of dynamic loading. Again, I can simulate these tests that may be hard to recreate with physical conditions by setting up this dynamic test. Here I used a random vibration study, which accounts for any loading that cannot be easily characterized. I may not know the vibration that the road will induce on the car and on this hitch, so this random vibration test will account for any high peaks in loading as well as any low values and everything in between. So I have the same model that we've been testing here, and I've also went and applied the loading that we've been working with, the 30 pounds from the 2 bikes on there. The other sort of loading, just like with the temperature, is I'm going to add this base excitation value. I'm going to set it as acceleration and give it a certain multiplying factor. Now I have options for the variation with frequency. I'm going to leave it at linear just for simplicity here, but we can easily define any sort of curve to represent how I want the random vibration to account here. Now the only other step is to define the damping. So I give it a certain value over the entire model, and then I let it run. Now the results are slightly different than we can see here. We do have our normal stress plot, and the maximum value does increase a lot, and you can see also the displacement plot does look slightly different than we've been seeing. And that's because this dynamic loading is different. It accounts for those bumpy roads, the vibration, anything like that. So you can see here that this deformation is what's causing that maximum stress value to occur. And you can see even in different areas those values jump up to. I do want to also take a look at the acceleration plot and figure out where that maximum value is occurring, which is inside with the bike hitch. So the car is experiencing a lot of the vibration, and right where it's attached is where it's going to experience most of its acceleration that you can see. Now I'll also take a look back at the displacement. I want to get just an idea of exactly how this loading occurred and what actually happens to this model. And I know this is the sneak peek that I gave you earlier in the PowerPoint. You can see here now exactly implemented with the study. And it came up quick and it happened right in the beginning, but you can see that that's the maximum loading and the maximum force that occurred from this random vibration. So it pretty much represents a large bump that this car could have hit. And that large bump causes the hitch here to deform in a certain way, which induces a certain amount of stress on the pins, on the bolts, and on the overall structure. So you can see it here in full view. Now you can see here the stress value did increase dramatically from what we've seen before and exactly where those locations are due to this type of dynamic loading. However, it is still below that yield value, if we can remember from the material, which is roughly 9.5 MPa. So even though it has increased and it has occurred this sudden bump, it is still within our potential yielding for this material. And again, you also have to consider that this is experiencing a load of, say, an extreme bump that it can take. So it's not enduring this type of loading constantly. So staying below that yield value for this material is safe to say that this model again can behave in the environment of going up a mountain or going on some rough terrain. So finally, the last study you're going to see here, and maybe one of the most relatable studies, is answering the question of how long this product can actually last for, its lifespan essentially. And this is a type of fatigue study that we can perform. It can be a pretty tricky test to actually do in physical conditions because we essentially have to set up our model and let it run for X amount of years, and then we can determine how long it'll last for. But that's super time consuming. So we can set up this fatigue study by giving it certain events. And in this case, the 2 events we're working with is the summer study that we performed and the winter study. So it'll count for all of the seasons in the year, extreme values on both ends. We give it a certain amount of cycles. We'll say 2,000 cycles, each cycle representing roughly a week, so a totaling of about 38 years in this case, so we'll test for. Again, like I'd mentioned, we have two events here. It's the summer and the winter event, and we're just going to run those both for 2,000 cycles. The only other useful information we need is to apply fatigue data to this material, which pretty much tells the software, under this loading and under the cycles, how does the stress value react to. After letting it run for the amount of cycles, we can get a damage plot out, which is in units of percentage, which essentially means that through those 2,000 cycles, how much damage did it use up? So 100% meaning that it has used up all of its life, all of its damage. Anything exceeding 100% means it has damaged it critically to the point where it has broken and failed. Anything below 100 means that it's still usable. There's no permanent damage caused on the structure. So we can see about 82% is our damage plot here, and where that is located, right around again where those pins where we saw that maximum stress value. So we can see in that area 82% damage caused on it, which means it is below the 100%, so it is safe to say that in the 38 years that we gave it, it's still going to be able to use it and it's not going to cause permanent failure. All in all, we can conclude that with the loading we gave it, this product has a lifespan of about 38 years that we can at least see confidently through our test. So now let's sum up what we did in this webinar. Previously, we looked at the different iterations this model went through to be able to determine if it was still in fact able to function the way that it needed to from its rough design. We were in fact able to reduce the model weight to 11 kilograms given the different type of modeling that we performed on it, such as that different support structure and the thinner wall thickness. Also, reducing it to the aluminum alloy as opposed to the steel it originally started with. And here you can see a little bit of a mock-up of a warranty through the testing that we performed. So we can see its maximum loading that is allowed to be placed on this before failure starts to occur. We're also able to determine its lifespan, something that is important when pushing out products and giving to the consumer end. Now all in all this validation and determining the environments it can work in took us the duration of this webinar, about 20 minutes of time spent doing these iterations, doing these design changes, and making the final tests, so that way you can confidently determine everything needed to validate your design. Thank you for your time, and thank you for watching this webinar. Again, I'm Lizzie Gryan, a simulation specialist with DesignPoint.